Was it the third one that was talking?
Oh, yeah.
Yeah, that one turned out to be smooth.
Okay, good.
Yeah, but I figured it out.
All right, so please, if you could, let's turn in the take home. Just kind of, I don't know, pass them, try and get them like this way.
When he helped me out.
Take one and then pass these back. The most fun? Is that what you said?
Most intensive.
Oh, they said most enjoyable. Did I put the wrong due date on there? No. Next Wednesday, yeah. Okay, any other take-homes? Where are they? Y'all got them over here? Okay. Thank you. Anybody else?
Oh, that's the next one.
Thank you. Okay, that's it. Okay, make sure you turn in your take-homes. And just set them right here on this corner. All right, we're gonna start a new section today, 11.5, chain rule. And there are not any notes that I usually hand out for this, just because, well, you'll see, it's a little easier to just write this by hand than it is to try and come up with a good image for it. So let's get started, all right? I will have some order to these notes, though. So first note, 11.5.1. Recall from Calculus 1, if y is some function of x, right? Then it makes perfect sense for us to talk about the derivative of y with respect to x, doesn't it? Yes? So we could ask for dy dx. By the way, did y'all have a good weekend? No? Okay, I'm sorry, Karen. You should have had it done. You should have got it done before Friday. Then you would have had a good weekend. Oh, I handed out the new take-home. I'm hesitant to say it because I said it about the last one. Like the last one, I was, oh, it's only 4 problems. This one's 6 problems. I think this one is a little more straightforward, just computational, not as much like trying to figure out what's going on. All right. So everyone have a copy of that? Yes? All right. It's due next Wednesday. So you get a little bit of a break. Yeah. So you can start it on Tuesday night.
That's exactly.
You should be able to do that entire take-home exam by the end of today's class. Everything on there is through today's stuff. Okay, so remember that when we were in Cal 1, if we said y is a function of x, then you could actually talk about what dy dx meant. Now I'm going to start doing stuff. It's going to look a little weird at first, but you'll see where we're going with this, all right? So I'm going to draw a little picture of what's happening here. I have y, and I'm going to connect it with the line down here to x. And what I'm saying is that y is kind of higher up on this diagram, x is below it, which means that in order to know y, someone needs to tell me what x is. So if I have x, I will be able to produce y. So this is kind of like the root, and the tree is growing out of this, all right? So it makes sense for us to talk about dy dx, since y depends on x alone, right? Someone gives you x, y can be determined, right? All right. Baby steps. Whoa. Need some more room up here. Now, what if you have this? 11.5.2. What if you're given that y is some function of x and that x is some function of t? I'll do it this way. X equals g of t. So y is a function of x. Shut it, please, yes. That means if someone gives you x, you can determine what y is, right? But over here this says in order to know x, someone has to give you what? T, right? So if I try and draw this diagram again, what would be the letter that would be the highest point on this diagram? Y. Okay, so we have y. Y would depend on what? It's supposed to be straight down. Y would depend on x. And x would depend on t, right? So when we link these two variables together, right, it makes sense for me to talk about the derivative of y with respect to x, doesn't it? And when I link these two together, it makes sense for me to talk about the derivative of x with respect to t. Yes? This all makes sense? And so back in Cal 1, if we were looking right here, y ultimately depends on t, doesn't it? Since y depends on t, which you can see it from this diagram also, right? T, you need t for x, you need x for y. Then we can ask for dy dt. That would be the rate at which y is changing with respect to t. So you change t by a little bit, that changes x, in turn that changes y. So we can talk about the instantaneous rate and change of y if there's a little bit of a change in t. Yes? We good? So what is this by the definition of chain rule from Cal 1? If I want to know what dy dt is, it would be dy dx times dx dt. That's what chain rule from Cal 1 would have told us. Now I'm going to give you an example of this right after this so you can see how this works, all right? But it's almost like these dx's cancel, don't they? Dx, dx, and you're just left with dy dt. Now, back in our picture, do you see that to find dy dt, what you do is you take the product of these two down the tree? Do you all see that? Now, we only have one branch to this tree right now. So it's hard to talk about it as a tree because there's only one branch. But we just multiply these two, and that would define the derivative of y with respect to t, yeah? Okay, so let's look at a specific example of this. Let's see, we'll call this 11.5. Example 1. there's nothing new here, okay, yet. It's just a different sort of notation. Let's say y is equal to x squared, and let's say that x is sine of t. Find dy dt. So what it'll be is the derivative of y with respect to x times the derivative of x with respect to t, right? That's what I just said on the previous note. And what is the derivative of y with respect to x? So come over here, take derivative on both sides with respect to x, and what would you get? 2x times now derivative of x with respect to t. So take derivative with respect to t on both sides. dx dt is equal to cosine t. And then what we could do next is get everything in terms of a single variable. Like right now I have x's and t's mixed, right? So I'm going to replace x with sine t. And this would give me 2 sine t cosine t, right? Now, of course, that's an identity, isn't it? Just so happens to be. That's sine 2t. What's that? What's wrong?
There was a problem like that from the test.
Oh,
There was a trigonometric identity like that.
yes, sir. I remember.
No one believed me.
No one believed that that was true? I believe you. I believe you. Are you talking about the one with trying to find the maximum speed? No?
Yeah, it was.
Okay. Yeah, so you could use this identity or you could have not. I think you could have left it like that also and still done it. But okay, all right, so look, this all seem okay to you?
Where did the X go?
This x right here? I replaced it. And that's just because I want everything in terms of t. So I just went back up to this right here. Now let me rewrite this problem in a different way, okay? I'm just change things up a little bit. What if I take this right here, okay, and I rewrite that, but let's actually just plug in x right now before we take a derivative. X is sine t, right? So this is really sine squared t. And if you were asked to take the derivative of this with respect to t, you would do chain rule, right? So the 2 would come out, be 2 sine t, then times the derivative of sine t, which would be cosine t, which is this answer right here, right? So that's this right here, what we did when we do this in Cal 1, this is chain rule, right? But now we're kind of looking at it from a different perspective. And you'll see why in just a moment. Okay, you just have to hang tight for a second. No questions? All right. So what if now 11.5.3 what if we have z is equal to some function of x and y? What do you need in order to determine the value of z? You need both x and y, don't you? So if I'm going to draw a diagram of this, I have z up top, but it depends on both x and y. So I would have to draw 2 lines coming off of this. This would be x, and then this would be y, wouldn't it? And let's think derivatives. When it came to derivatives of this from last class, we said that there were how many different derivatives we could get from this? There were 2 that we talked about. One of them was the partial with respect to x. The other one was the partial with respect to y, right? So what happens in our diagram is if we're going to try and talk about a derivative going from here to here, or a derivative going from here to here, it can't be a straight derivative like in Cal 1 because we're holding one variable constant. So we call them partials, right? And our notation would look like this. Partial of z with respect to x, right? That would be down this branch. And then down this branch, partial of z with respect to y. Does that make sense? Those are the two derivatives that are possible. Right? Those are the two derivatives that are possible. So anytime you have a diagram where a single variable needs two different variables in order to determine, right, what the value is, down those branches have to be partial derivatives. They cannot be straight derivatives like Cal 1 unless the branch goes down by itself like in the previous problem, right? Then they were straight derivatives. Got it? Okay, so let's do an example. I'll do it next to this. Example 2. Let's say z is equal to x sine xy. Oh, I've fallen behind on the homework videos. It's just been busy. Well, yeah, I've had some things come up. So my plan is to stay after today, after class, and I think I'm going to try and do 11.4 and 11.5 homework videos. Okay, example 2. So let's find how many derivatives are possible here. 2, right? That's it. Because z depends on x and y, so there's 2 derivatives possible: partial of z with respect to x and partial of z with respect to y, right? So let's start with the partial of z with respect to x. This would be equal to, I'm going to hold which variable as a constant? Y. So that means I'm going to have to do what when I do this here? Product rule, right? So product is right here. Derivative of x is 1 times the other one, plus now derivative of this one, cosine xy. Then go inside, what's derivative of xy with respect to x? Y. And then finish off product rule, x. We did that last class, didn't we? So this is sine xy. I think I'm just going to clean it up a little bit. Xy cosine xy. Okay, so there's your partial of z with respect to x. Questions? Okay, now let's do the partial of z with respect to y. So what is it? Okay, x squared cosine xy. Do y'all agree? So x is a constant now, so there's no more product rule, right? Because x is a constant, it's just covered up, it'll come for the ride. Derivative of sine of xy is cosine of xy times the derivative of what's inside. What's that derivative of this with respect to y? Just x, right? So that pops out, but I already had an x out there, so x squared. So that's correct, good. All right, so these two partials are different, right? Okay, so nothing new on this, really, just some different notation, having you draw some trees. So what if I tell you this? This is, now we're moving into the next note. The whole idea here is to get to a chain rule. Some way of taking derivatives of really complicated functions that depend on other functions. Okay, so how about this? Suppose you have z is some function of x and y. And, so I'm going to use comma for and x is some function of t, and y is some other function of t. What do you need to know in order to know what z is? T, and that's it? You need to know x and y, right? But if I give you a value of t, can you tell me what z is? Yes? Because once I give you t, don't you know what x and y are? And if I know what x and y are, don't I know what f of x and y are? See, that's different than the last problem. The last problem looked like this. In order to know what z was, right, you had to know x and y to get z. This problem's different because x and y both depend on t, right? So let me try and draw a picture, a tree. Where did it go? There it is, right behind me. Let me try and draw a tree of what's happening here. I have z on top, right? In order to know z, I need to know x, I need to know y. What do I need in order to know x? T. What do I need in order to know y? T. You see that to get from the bottom up to the top, all you need to know is t? Yes? So let's talk about, yes, question?
Is the t going to be the same for both of them?
It'll be the same t. So you could, and I've seen some people draw it this way, is they put them like this. You could do it like that. Do y'all like that notation? I can go with that notation, yes? I think that's a little different than the book, but I think we can all agree with that. That's all right? So if I know t, I'll be able to get all the way back up to z, yes? So z depends on just t, yes? So what derivative is possible? dz dt. dz dt. So partial or just, or straight? Let's think about this. A partial derivative is only used when we have to hold one variable constant, right? Here, I don't have to hold a variable constant because they share the same thing. They get their values from the same place, right? T goes in, x is determined, y is determined. Those come in and get you z. So z depends exactly on t instead of in the previous problem where z depended on two different things, right? You have to give them both. Okay. So this derivative is possible. The question is, what the hell is it? What is it then?
dz dy times dy times
You can go either way.
Yes, you could go here and here, but look, it could get a lot more complicated. That's what we're trying to do is come up with a general pattern or formula that will work. Okay, so let me come back to this tree, and now you'll see kind of why I did things the way I did earlier. Do you remember I said if you're ever going to go from a variable to split across, if you're going to talk about the derivative along this branch, it'll have to be a partial, right? So you agree to go from here to here as a partial z with respect to x, yes? And do you agree over here would be partial z with respect to y, yeah? Now, what about going down the branch here that goes from x down to t? Is that going to be a partial derivative or a straight derivative? Straight. Straight, because it's going to be x depends just on t. So this is dx dt, understand? And down this way, it's what? dy dt. Okay? Any questions on that? Now, let's imagine that y wasn't here. Isn't that the problem I gave you a minute ago where z depended on x, but x depended on t? And what did I say the derivative of that was? Do you remember? Yes, and you just multiplied those two pieces together, didn't you?
Yeah.
Right? Now we have two pieces instead of just one. See, this was chain rule right here. It was down here. We do that times this. But now that we have another branch, here's what we're going to do. dz dt is going to be the partial z with respect to x times dx dt. So that's this branch, right? Plus, okay, plus the product down the next branch, which is partial z, oops, that's a partial y. What's that? I didn't hear that. Did you say that's just wrong?
No, that's just bizarre, man.
Yeah, it is kind of odd, but look, if let's just say for the sake of trying to make it make sense as to why this works and why this is not multiplication, because that might be your question, like why isn't that multiplication? Just chain them all together, right? Maybe. I don't know. Think about it this way: what if y is the zero function? Okay, so y is gone, really, right? Because the derivative of 0 is going to be 0. You should still have a derivative. You should still have something. And so if y is 0, this whole side is gone, isn't it? And all you have is this. But if x is 0, This should be gone, but this should still be there, right? This is the way you can make that happen with addition. So if the y function's gone, this part's gone, you still have derivative on the other side. Here, if that's 0, you come to the other. Does that make sense? So that's why there's addition between the two. All right, so let's do an example of one of these. And we're going to go back and we're going to look at the same one we just had. That'll make our life a little easier when it comes to these derivatives. X sine x, y. That's what we had before, right? The problem right before this. But I didn't tell you anything about x or y, right? I just said that's it. Now I'm going to tell you something a little bit about x and y. X is going to be t squared plus 1, and y is going to be natural log t. So let me act like I'm just starting this problem. All right, I'm sitting there, I open up my book, and I'm doing a homework problem, and I look at this, and it says, the question is going to be, what derivatives are possible? Okay. I think this is, where's the take home? Can I look at that real quick? Slide over. This is very much like number 6. Determine what derivatives are possible. Draw a tree diagram and label all branches. Find a formula for each possible derivative, and then find each derivative. So that's pretty much the way you want to approach this. All right. So first of all, what derivatives are possible here? So the way you answer that question is you look at the top variable, which we said was what? Z, and you look at the bottom variable. There might be 1, there might be 2, there might be 10. What's the bottom variable here? T, right? T is the bottom. So as soon as you know that the z can be determined from t, ultimately, there's only one derivative possible. It's the straight derivative dz dt, right? So I like to draw the tree first before I determine z, x, y, t. So dz dt is only possible derivative. Do you have any questions on that? Then you come through. I know we just did this a second ago, but I'm doing it again. We say, hey, z splits apart, so I know if I'm going to go from here to here, it has to be a partial. Here, partial. X to t, there's only one line going there, so this is straight. Same thing over here. This derivative will be, what's some language I could use here? This derivative should be the sum of the product of the branches, right? The sum of the product of these branches. So dz dt should be the sum of the product. Here's the product of the first branch plus the product down the second branch. There. And let's actually compute this now. What is the partial of z with respect to x? We did that just a moment ago, didn't we? Yeah. Partial of z with respect to x. It turned out to be sine xy plus xy cosine xy, right? That was just that piece, right? I'm going to put that in parentheses. Times, now what's dx dt? Come up here, dx dt, right there, 2t. Understand? What's next? Add, so plus. Now, partial z with respect to y, which was, we did that a second ago. What was it? X squared cosine xy. And then times dy dt, which is 1 over t. That's your derivative. However, z depended on t, right? which means that my answer should just have t's in it. So what I'm going to do is just go back to this, and everywhere I see an x, I'm going to replace it with t squared plus 1. Everywhere I see a y, I'm going to replace it with natural log t. I'm going to write the whole thing out. That's the derivative. I'll put it right here. So this dz dt is equal to sine of, so I'm doing this, x times y, so that's t squared plus 1 times y natural log t. That's just that, right? Plus, what's x times y? Shit, again, t squared plus 1 times natural log t. But then that's times cosine of, again, t squared plus 1 times natural log t. Close off my big parentheses. Yes or no? Yes? It's just tedious at this point, isn't it?
Yes.
Then this times 2t. Now I could distribute the 2t through these, but I'm just going to leave it for now. I'm only right here, right? That's where I am. I'm right here at this point right here. So then plus, and then this right here. So I'm going to need a new line for this because I don't want to go off the screen. So plus x squared, which is this squared, so t squared plus 1 squared. And then cosine xy, well, I had that already. Cosine of, here's x, here's y. And then finally, times 1 over t. That's it. That's how chain rule works when you have functions of more than one variable. Questions? Yes.
So, like you were saying for the other problem, if you replace x and y with the functions to begin with, and then took the derivative,
Mhm.
you'll end up with the same. Or
Yeah, let's see what would happen. Let's just look at it. We're not going to do it, but let's just take a look at it. What you're suggesting is, let's look at z equals x, which is t squared plus 1 times sine of x, which is t squared plus 1 times y, which is natural log, sorry, yeah, I got that right, natural log t like that. There's the original function, replacing x with t squared plus 1, right, and replacing y with natural log t. If I ask you to take the derivative of this right now, you could, right? And it would be, you would have product rule here, right? So you'd start doing that, but then when you realize when you get to this part, when you go chain rule inside, you've got another product rule. And it would be a mess, but you could do it. Like that would be a good exercise for you, you know, if you were just wanting to have fun, I guess. But this is the way you can do it. It's a little bit cleaner. It's a little more systematic. And as you're about to see, there's nothing stopping us from going even further back. So like what if t depended on some variable r and I don't know, maybe r depended on two other variables, s and t. So I mean, you could have a lot of different things controlling a lot of different variables in many different ways. The key is, can you draw a picture? Can you draw a tree diagram? If you can do that, you can find the derivatives. So, all right, let's look at another one. 11.5. This will start to get pretty interesting. 11.5. Let's say that z is some function of x and y. Let's say that x is some other function. What am I using here? G of Rs. And let's say y is some function h of Rs. First question, what derivatives are possible? or what derivative, or derivative is plural, I don't know. We have to determine that. What's possible? How do you calculate them? What's the formula for each one? Right? Okay, so let's start with the tree. What do you need in order to determine z, right? What do you need to know? Well, z, you need x and y, don't you? What do you need for x? R and s. What do you need for y? R and s. So can I just give you R and you tell me what z is? Can I just give you s and you tell me what z is? No. You have to have both, right? And if you have to have both, then this means the only thing possible should be partial derivatives, right? But let's try with the diagram. Start with this. Z on top. How many things do you need to know to determine z? X and y. What do you need in order to determine x? R and s. And over here, R and s. Now this is why I like to keep my tree diagrams split. This is why I don't like doing this right here. You said you like that notation, right? And I said that, you know, the way that I like to do it is this way. It's only because, look, these both rely on R and S, right? Don't they? So you might try and draw some cute way of making them both go to R and S, but you're going to get things crossing over each other. It's going to be complicated. So even though it's nice to be able to put these both to T, if you just keep them separated, you're going to get the same picture at the end, like the same products, but you don't run into problems later like you would here if you try and connect those. So, okay, thank you. Anyone else? All right, so there's my picture, right? So ultimately, z depends on r and s. So the possible derivatives are what? Since z depends on r and s, you have two different ones, right? You have the derivative of z with respect to r and the derivative of z with respect to s. Are they partials or are they straight? They're partials. And the reason they're partials is because it splits, okay? Like in order to get from z down to r, right, you have to go this branch or this branch, right? So because there's a split, they have to be partials. So one thing that's possible, partial z with respect to r. And the other one is the partial z with respect to s. Now let's try and come up with a formula for the first one. Okay, so let's try this one. Partial z with respect to r. What does your gut instinct tell you it should be here? Or do you want me to fill out the tree first? Should we fill out the tree? Let's fill out the tree, and then I'll ask you that question. So just start trying to fill the pieces in. How do I get from here to here? What kind of derivative between here? Partial, right? Because it splits. So partial z with respect to x, okay? Keep going down on that side. Partial x with respect to r, right? Because again, x splits, doesn't it? So this has to be a partial. Okay, down this side, partial x with respect to s. I'm running out of room here. How about this one right here? Partial z with respect to y. How about this side right here? Partial y with respect to r. I'm gonna just move this out a little bit. Y splits out. R, S. So partial y with respect to r, and then this side, partial y with respect to s. Understand? That's the whole tree filled out. So what did you think this one was going to be? Did you have an idea?
Partial z, or no, yeah, partial z over partial x
Okay.
plus times partial x over partial r plus partial z over y and times partial y over r.
Yes, you got it. So this is it. This is what we're going to do. We need to go, since we're going from z's to r's, right? I need to come down all branches to get me down to these r's. So I need to come down partial z with respect to x times, because I'm coming down a branch, partial x with respect to r. That'll get me down this way, right? Plus, then I come down to get to this one, down here, into there. So it'll look like this. Coming down this way, partial z with respect to x times partial x with respect to r, plus partial z with respect to y times partial y with respect to r. Notice that we don't even look down the partial x with respect to s and partial y with respect to s. The reason why we don't do that is because if you're looking at the partial of z with respect to r, what are you holding constant? You're holding s constant, aren't you? If s is a constant, right? If s is a constant, right? If s is a constant, then this branch right here, right, is going to be zeroed out when you take a derivative. So it's not even going to matter. So there it is. Now, let's do the other one. Let's see if there are any other colors in here. I don't see green. Let's do partial z with respect to s. So what would the difference be in my picture? There's a green one over there? Oh, there we go. Good. There's one where? Oh, I didn't see that one. Okay, so the only difference here is that we got to get down to the s's, right? So the path we take still starts here. We're going to come down here, and this time we're going to go down this side. Come down here and this side, right? So the two pieces that'll be the same are the partial z with respect to x will still be there. The partial z with respect to y will still be there. These two pieces are going to change with respect to s and s, yes? So partial, I'll do it in green. This is partial z with respect to x, but now partial x with respect to s, plus partial z with respect to y times partial y with respect to s. Those are the two derivatives that are possible, and there's the formulas for each one. Is this clicking? Yeah? Okay. Let's try and compute one of these. Let's do an example. What example is this? Is this example 3 or 4? Example 4? All right. Ah, come on. Okay, z is equal to x sine xy. X is equal to t squared plus 4, oh. Okay, x is equal to r squared plus 4s. And y is equal to the natural log of r times s. rs. That's multiplication in there. So if I'm starting this problem out, first time I'm looking at it, z depends on x and y. Okay, x depends on r and s. Y depends on r and s, right? So I'm going to draw my quick tree. See, at some point this becomes quick. X, Y, R, S, R, S. And so the possible derivatives, there's two of them, right? I'm only going to do one of them, all right, because I don't have time for both. We can do partial Z. You want to do it with respect to R or S? R. Which, if I follow my tree down, I'm just going to show the tree, the pictures for this particular one. Partial Z with respect to X, partial X with respect to R. Then I'll do partial Z with respect to Y. That's a terrible marker. And then partial Y with respect to R. So this is partial Z with respect to X times partial X with respect to R plus partial Z with respect to Y times partial Y with respect to R. You ready? This equals. What's the partial Z with respect to X? We've done this already, right? This was sine X, Y, plus XY sine X, no, cosine XY. Okay, that's just this piece. What's the partial of X with respect to R? Well, that's a nice one, right? S is a constant, so just 2R. I like that. Plus, what's next? Partial Z with respect to Y. We've done that already, right? X squared cosine XY. And then partial, yes? Partial Y with respect to R. What's the derivative of natural log of RS? 1 over R times S times the derivative of the inside with respect to R, so hold S constant. What's the derivative of RS if S is constant? S. And the S's cancel here. So this is just 1 over R at the end. And then what would you do? Replace all your X's with R squared plus 4S, all your Y's with natural log RS. You rewrite the whole ugly thing, and that's your derivative. It will have two variables in it when you're done. What should those variables be? R and S. That's it. Got it? Okay. You sure you got it? You think you got it? Yeah, I mean there's no hidden magic in this at all, all right?
That's all we do, like find the partial derivative for C with respect to R and then Z with respect to
Yeah, there would have been another one. Just because of time, I didn't do it.
So then what do we do with those? Those are the final answers?
That's it. All we're trying to do is say, is there a way to find the derivative of a function that is actually a function of more than one variable and depends on things that might possibly be a function of more than one variable? Does it still make sense to talk about instantaneous rates of change? I mean, we know when you go back to Cal 1, right? I hate to go back to this and keep harping on it, but when we have a function, right, and you're trying to find the derivative, it represents the slope of the tangent line. It was the instantaneous rate of change. It was dy dx, yes? The way we got that is we imagined a separate point over here, and we drew a right triangle, and we basically said that this base side was the change in x, delta, and this was the change in y, right? And so when you do like slope of this line, it's going to be the change in y over the change in x. And then if you let this triangle get infinitely small, right? Infinitesimally small, this delta x became dx, and this became dy, and that gave you the derivative, dy dx. And that's what happens when you move that point on top of the other one. So the idea was that if x changes just a little bit, right? If I just move a little bit to the right, then my function is going to go up or down, right? And that change, that slope, that change was the derivative. So if x changes, y changes. And this represents the amount at which the amount that y will change. This is saying if z depends on x and y, and x depends on r and s, and y depends on r and s, then if I just move r just a little bit, right? If I just allow r to just change a little, how much will z change by? That much. You see? That's the formula to compute that change. If I change s by a little bit, how much will z change by? And so it's still an instantaneous rate of change. Does that make sense, Kieran?
Yeah.
Okay.
I just wanted to know like what you're trying to get.
Yeah, we're not trying to now like solve and get a number or anything. It's more of, can you come up with a formula that will represent the derivative? We actually aren't even going to really mess with it too much. But this is a generalized chain rule. This is what it is. It's a generalized chain rule, which is why this section is called chain rule. You could almost in Cal 1 have started with this idea, but of just drawing a picture. It just would have been too much. So you ready to try and generalize this? Yes.
When we're at the end, when we have to rewrite it,
Uh-huh.
in terms of like R and S,
Uh-huh.
we have a function that has S, R, and S in it. Do we have to adjust that, or are we leaving it both?
If it has a function that what?
Like x was R squared plus
Mhm.
4S,
Uh-huh.
and we solved for R on one of
Mm-hmm.
them. Are we still leaving that S in there?
Yes, you would have R's and S's in your answer. And that's because you're holding S constant, right? But in order to actually find the derivative, you would have to know what that constant was being held at. Okay, can we come up with a general idea, a general formula for this, all right? So let me try it by drawing a picture. Right, what if we have z up top, right? And z depends on a couple of things, right? Like x and y, or maybe it depends on more than just x and y. How about if z depends on x1 and x2 and x3 and ... all the way out here to xn. So let's say z depends on n different things. We've only dealt with one case. Well, we've dealt with two cases where z depends on one thing or z depends on two things, right? X and y. But what if z depends on n things? And what if each of these depend on, let's say, t1? And this one depends on, let's say, t2. And let's say to tm. Now, I'm not going to use n and m. These are different numbers. Because this one might depend on three things, where this one might depend on five things. Understand? So I'm using subscripts instead of x and y because if I use subscripts, I never run out of letters, right? This x2 also depends on t1 through tm. This x3 depends on t1 through tm. Make sense? This xn depends on t1 through tm. What derivatives would be possible here?
With too many.
What derivatives would be possible? dz. So z. What does z depend on here? What does z depend on? Depends on ultimately t1, 2, 3, all the way to tm, right? Yes? So what's possible here is partials of z with respect to t's, right? I'm going to say ti's for I equals 1, 2, all the way out to what? M. Do you agree with that notation? This is what's possible. There are how many partial derivatives possible for this situation? M of them, right? I could have partial of z with respect to t1. partial of z with respect to t2, t3, t4, all the way out to tm. Yes? Can you give me a formula for the ith one? For the ith partial derivative. Let's see if we can. So let's just pick one. Let's just pick an I in here. Do you agree that a ti would be somewhere in here? I mean, if I is 1, of course, it's the first one. If I is m, it's the last one. But we're just trying to come up with a general formula. So there's a ti in here. There's a ti in here. There's a ti in here. So what would you have to do? You'd have to get down to each one of those, wouldn't you? Yeah? So let's go down. Let's get to this one. What would it be? What's this branch right here? Partial z with respect to x1. And then down this branch right here. Partial x1 with respect to ti. Right? Plus, then you have to come down this way, which would be partial z with respect to x2 times partial of x2 with respect to ti. And then you do it the rest of the way. Make sense? How many of these you would go all the way out until you got to partial of x? Okay, so let's see if I can write this out. I don't know if you'll be able to keep up with this. Let's see. I have to erase the picture. Oh, maybe I can put it down here. The partial of z with respect to ti would be equal to, like you just said, partial of z with respect to x1 times partial x1 with respect to ti plus partial x2 with respect to, partial what? I screwed that up. Where am I? Coming down this branch now, right? Partial z with respect to x2 times partial x2 with respect to ti. Y'all still there? Do another one. Plus partial z with respect to what? x3, so I'm coming down this one now. x3 times partial x3 with respect to ti, right? Plus, I keep doing this, until I get to the very last one, which would be the partial of x sub n, z, over partial x sub n times partial x sub n over partial t sub I. That would be it. Go ahead. You don't have to explain. Go ahead. This good? That's a general formula. Now, just out of curiosity, what would happen if each of these t's depended on like R1, R2, all the way to like R, let's see, I've used N and M. How about if I go R sub K? You would have another piece to each of these, right? But even more than that, you would have an additional branch for each one. So like, you would have to go down here, and then once you got here, you'd have to go down each branch. Oh, man, disaster. But you could see how this could generalize, right? And there's no restriction now how many variables your z depends on. It can depend on 1,000 variables, and each one of those depend on 50, and each one of those on 10, and each one of those on 20. And what happens is you can still find a way to determine instantaneous rates of change. You just got to be able to tree it out and figure out what branches to go down. All right? Exciting stuff. I'm just trying to decide how I want to show you the next thing. So we're going to change it up here just a little bit. Implicit differentiation. Now, we've seen implicit differentiation before, right? This is not the first time we've ever seen this before. I'll ask you to remember, recall, from Cal 1, if you had something like xy squared equals sine of x plus y, then it would be impossible for us to isolate y. So we would use implicit differentiation, and what we could do is we could find here, dy dx, right? We'd be able to find that. We could also do dx dy if we wanted to. If we do dy dx, that means we treat y like it depends on x, and then here we treat x like it depends on y. And so we take a derivative on both sides, right? That's the way implicit worked. Should I work through this or no? No? Okay, so just recall that. Now what we're going to do is, let's say that we have our goal here. Let me show you the end first, and then we'll see how we're going to get to it. Our goal here is to take something like 6xyz. X cubed plus y cubed plus z cubed plus 6xyz equals 1. And to find in this the partial of z with respect to x and the partial of z with respect to y. What's that? Yeah, so how did we do the partial of z with respect to x? We held y to be constant, didn't we? And there what we were saying is that z depended on x and y, right? So what we've done before, okay, before this problem, what we had done before is if I gave you something like z was equal to x sine xy, right? This is the problem we've been messing with. We could find the partial of z with respect to x, and the way we did it is we took the derivative of the left side with respect to x, which was partial z with respect to x, yes? And then on the right side, what we did is we held all our y's constant, and we did the product rule, and we got sine xy plus xy cosine xy, right? That's it? That's what we did? So we did left side and then right side. Why can't you do that here? Okay, the z is not isolated, right? The z is not isolated. So we could just come through here, right? We could come through here and do, what's the derivative of x cubed with respect to x? 3x squared. Derivative of y cubed with respect to x. So we're treating y as a constant. So derivative of that? 0. Derivative of this? 3z squared. Partial of z with respect to x. Good. Here, what would you have to do? Y is a constant, so you'd have to do product rule in here, yes? So we could do this, okay? We could, but it's not as clean as this one is, right? This one's just here, and then do this, and then we're done. But because the z's mixed in with this, it creates more of an issue. Do you all understand that? So what we're going to try and do is we're going to come up with a formula that will allow us to do this a lot easier, okay? Rather than having to go through all this tedious stuff, all right? So let me see if we can come up with this formula. I hope it works out, okay? All right, so the road to a formula. Let's try and get road to a formula. All right, let's suppose, have I shown you all that symbol? I know some of you I've shown. In mathematics, that's what we use, S with a little line, that's what we use for the word suppose, all right? So suppose we are given something like this. Z is some function of x and y, all right? Let's say we are. Then what I'd like for you to do is I'd like for you to move, just look at it as an equation, move it to the other side, and do you agree with this? Do you agree with that? Just algebraically move it to the left? Yeah? Okay. We are going to take this left side of the equation right here. Notice that there's a 0 on this side. I'm going to call this, I'm going to define this to be capital F of x, y, z. I'm using capital F so you don't mix it up with this little f. But I'm not saying that this is the antiderivative or anything like that. Just I'm going to call this entire side, the left-hand side of that equation, capital F of x, y, z. Okay? Now, the next part is I would like for you to draw me a tree for this situation right here. Tree. If I want to know what capital F is, what does it depend on?
You have 3 branches.
I have x, y, and z. Do y'all agree with that? Yes? Okay, now this is the part that's tricky. Remember the idea here. How can I do this? Let me get the problem that was the goal up here. Remember this was our goal? That was our goal, is to be able to find the derivative there. If I give you x, or let's say, I knew I was going to have trouble with this. We are assuming that y, all right, that z depends on what two things? X and y, right? Agreed? Because that's from here. Now, we did this, we all said that z must depend on x and y. Yeah? Now, this is the tricky part that doesn't seem natural, but let's just draw it. You know how the bottom row of our tree always had the same thing in it? Like it was either all t's or all r and s or whatever? I want to make all my branches here have the same values. Now just watch for a second. X depends on x. That's obvious, right? Y depends on y. That's obvious. This is not so obvious. Y depending on x and x depending on y. Right? That's not as obvious. But in some sense, if z is given up here, right? If z is given, then you could isolate. You could say that y and x would be left, so y somehow depends on x. You could also do it the other way. If z is given, then you could have y and z, or x and y in there. You could say x somehow depends on y. So these two are not completely out of the realm of like rational thought to think that that would be okay. Let's just see where it goes. All right, just bear with me. What derivatives are possible here? So tell me what derivatives would be possible in this tree.
Partial left, partial right.
What's possible is possible would be partial capital F, right?
Right.
partial capital F with respect to x, and partial capital F with respect to y. Nope, because look, the bottom row is what we're going off of, right? Because if I know x and y, then I'll know z and back up. All right, let's look at the partial of f with respect, capital F with respect to x. Let's look at just this one. Partial capital F with respect to x would be equal to, I'm going to go down which branches here. Go down here, right? And then down here, right? And then I'm going to go down here and down here. And then down here and down here, right? Those are my branches. Questions? Okay, let's try this first one. Here to here is partial of f, capital F, with respect to x. What about this branch? Partial x with respect to x. That's like dx dx. What's dx dx? It's 1. So, but that's not going to matter. I mean, we'll get to that later. Then I come down here, partial capital F with respect to y, and then partial of y with respect to x. Yeah? And then this one, partial capital F with respect to z, and then partial z with respect to x. So it's very similar to what we did before. Yeah? All right, let's write this formula down. This will be partial, god dang it. What is it? This times this, right? So partial f with respect to x times partial x. I'll write down partial x plus down this way. Partial f with respect to y times partial y with respect to x plus one more. Partial f with respect to z times partial z with respect to x. Y'all still with me? What is this equal to right here? 1, that's a 1. So can I erase it? Okay, that's a 1. Aren't these the same? Subtract it on both sides. Right? I can subtract because this is addition between those. If I subtract this on both sides, I get a 0, don't I? So I'm going to get 0 equals partial capital F with respect to y times partial of y with respect to x plus partial f with respect to z times partial z with respect to x. Now I know I've kind of taken us on this weird journey, okay? But I'm going to take you back just before we continue here. I want to take you back to our goal. Our goal was to try and look at that and find two different things. Partial z with respect to x and partial z with respect to y, which would be easy to do if we could solve this for z, right? We can't solve it for z, so we're trying to use some sort of implicit differentiation. So I did some weird shit, and then now I'm doing all this, and I've gotten us to here. And you're like, okay, now what? Let's just focus on this one. Do you see that in there? You see it? Yes? Okay. I would like for you to go ahead and solve for that. So take the other stuff to the other side. What do you get? So I'll move this to the other side. You get negative partial f with respect to y times partial y with respect to x equals partial f with respect to z times partial z with respect to x. We agree? Now, trying to solve for this, right? Divide, so take this, put partial f with respect to z, and then this side becomes this. Yeah? Okay, one more thing. What's it? Yeah? Yes, what? This right here. Right there. Okay, so we're almost there. Hold on, we're almost there. We have you mean like flipping like this? Hold on, let me see what are you going to get if you cancel them?
Negative dz over dx.
Yeah, that's what I thought.
Yeah, you're going to get this appearing on the other side, aren't you?
And we don't want that.
You don't want that. What we want is a formula for this that involves something else. So leave it the way it was. On the top we have negative partial f with respect to x over partial f with respect to z. That equals partial z with respect to x. Let me just double check that I got that. Partial f negative x, partial f with respect. Okay, perfect. All right. So that's a formula for this. All right? Box that up. That's it. That should be something you have copied down somewhere. It's in the book also. Now, I'd like for us to go back to the tree that we just had. And let's talk about that other derivative that we could have found. You remember the tree? It was f, x, y, z. You have this written down, so. We had done a formula for partial f with respect to x just now, right? We could go with respect to y now, if we wanted to. And that would take us down here, 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 right? Can we write a formula out for this then? Partial f with respect to y equals, so come down this way, yeah, this way. So partial f with respect to x times partial x with respect to y plus partial f with respect to y times, are y'all following me or am I just talking to myself up here, right? Are y'all still there? Okay. Partial f with respect to z times partial z with respect y. That's what it would be. And look, what I'm trying to get at now is, can we get a formula for this? Do you see that in there? See it right here? Right? Do you see that? Can you isolate that? So which one of these is 1? This right here is a 1. And when I subtract this on both sides, right, this one, subtract, I get 0 again. Very similar to what just happened a second ago. So 0 equals partial f with respect to x times partial x with respect to y plus partial f with respect to z times partial z with respect to y. And then move things around and solve again. And you should get a formula. Anybody have it? Want to go out on a limb and tell me what the formula is for partial z with respect to y? What do you got? Negative partial f over partial x over partial f partial z. Who's in favor of that? All of you? No. Yes? Yeah, that's it. Negative partial f with hold on. Hold on. No. This is y. This is y right here? Yeah, this is y. Do y'all see that?
Yeah.
Okay. So we agree with that? Yes? Okay. All right. So that's it. You got them both boxed up? I'll write them down over here. Partial z with respect to x equals negative partial f with respect to x over partial f with respect to z. Is that correct for that one? Yes. And then this one, partial z with respect to y equals negative partial f with respect to y over partial f with respect to z. Those are our two formulas. And now let's go through and do this problem. How much time do I have? 20 minutes. Perfect. All right, what we'd like to do is take that and find these two partials. Right? The first thing I'm going to do is move everything to one side and make it look like this. Bring everything over. Minus 1 equals 0. Okay? Is that all right? Yes? Minus 1 equals 0. This right here is capital F of x, y, z. Let's find these two things. So let's start with this one. What's the partial of z with respect to x? According to our formula, it's the partial of this f with respect to x, which means what? Partial of this with respect to x. That means we're treating x like the variable, y and z as if they're constants. So I'm holding y and z constant and looking at just x being the variable. What is the derivative of this if x is the variable and y and z are constants? So what's the derivative of that? 3x squared. So negative, let's do negative. 3x squared. What else? 0, 0, and then
Minus 6.
plus 6 yz. Okay? Got it? And then over the partial of f with respect to z, which is the same thing. You're going to let z be your variable and let x and y be your constants. So 0, 0, 3z squared plus 6xy. We good? Distribute negative 3x squared minus 6yz over 3z squared plus 6xy. There it is. That wasn't so bad, was it? Do you see how quick that was? Okay. Now we could do the other one. Let's do partial z with respect to y. So we're going to do partial of f with respect to y with a negative out front. So how about that? What's partial of f with respect to y? 3y squared plus 6xz over, now the partial of f with respect to z, which we already did, didn't we? 3z squared. You see how quick those two were? Now that we have the formulas? Now I want you to appreciate that, so I'm going to make you appreciate that right now. You ready? I'm going to act like those formulas didn't exist, and I'm going to do the same thing. I'm going to find this one right here by going about it the harder way. Here it comes. You don't have to write this down. Let's just see it. I'm going to take the partial of z with respect to x. So that means I'm going to treat y like a constant, z as if it depends on x, and x as if it's my variable. So what's the derivative of this? 3x squared plus derivative of that plus derivative of this, partial z with respect to x, plus Derivative here. Product rule, right? So derivative of this with respect to x, which is 6y, times z, plus derivative of z with respect to, or partial, z with respect to x, times 6xy. I'm going to run out of room. Do you understand that that was product rule right here? And then derivative of -1 is 0, equals 0. Equals 0. Now let's isolate these. So everything that's not those to the other side, which is what? This piece and this piece. Let's take it to the other side. So that would be -3x squared minus 6yz equals whatever was left over here, 3z squared partial z with respect to x plus partial z with respect to x. I know I'm working through this fast, but I'm hoping you're just following what I'm doing. What can I do on this side? Factor out, so partial z with respect to x, and then I'm left with 3z squared plus 6xy equals this side. Divide this over. Does it match? Does that match this?
Yes.
Yes. See, that answer matches this answer? I would argue that this is a little more work once you have the formula, right? And this can get really complicated now, and this is much easier to calculate than that one is. So it's kind of a shortcut for taking derivatives of equations of two variables. Equations containing three variables. All right, we got about 10 minutes, but I think that's probably good for 11:05. What do y'all think? Yeah? I'll give you some time. Let me look over this thing here. So on number 4, on your take-home, number 4, you see number 4 on that take-home? Anybody not have a copy of the take-home? There weren't any extras floating around? Raglan, you got a copy? Yes? The take-home, the new one?
The new one,
No?
no.
There's not another one? Okay, here we go. So if you look at number 4, number 4, find partial z with respect to x, right? Looks a lot like this, right? Partial z with respect to x. So you can do that the hard way, or you can do it the easy way. Or you can do it both ways just to practice. All right? Number 1 on the take-home. Okay, so on number 1, you're looking at a domain problem, sketching the domain. I think that's straightforward. There's no magic to that. Number 2 also is just practicing some partial derivatives. And those are higher order derivative. Well, no, it's not even, I don't even have you go that high. Partial with respect to x, then y, then xx, then yy, then xy. All right. No big deal there. 3, that's just like a notation thing. Do you understand what that notation means? Like the order of that? Do you know what order to go in? And then 4, we just talked about. 5, equation of tangent plane. You had a problem at the end of class that y'all did that y'all worked on together, right? Last class? Right? Do you remember the problem at the end of class last time where you had to find the equation of a plane? And okay, so that's like number 5. And then number 6, that's straight. Does that seem like a pretty straightforward take-home? Yeah?
Well, no, I guess.
You'll know. I mean, it might get kind of ugly once you get in there, but it's not like the last one where it's like the particle moves along a path 4 units, and and you're trying to figure out what the hell does the 4 units mean, and there's nothing hidden in there. It's all direct questions.
We'll find out on Tuesday.
You'll find out when you start Tuesday night. Yep. Yes.
Wednesday morning?
Are you going to get what?
The question back?
Yes, I haven't touched anything like since Thursday. So you will get those back. Yep. All right, everyone. We're going to cut out 10 minutes early. What was what? For number 2? I can tell you what I have. The actual distance from number 2. $3.29. No? That's what I got, 3.29. No, you didn't get that? Yeah. I'd go back and double check. We'll see how if anyone gets 3.29. Let me turn this off real quick.
A question about